Thank you for the invitation. This is a huge honor. I've never done this before. I wish this could be in person. I would definitely love to visit in person at some point, um, but this is also a huge honor. So the the sort of my original mother tongue is Bengali, but I also know Hindi, and I know there's one word in common for sure between Farsi and Hindi. So, shukran. Thank you for having me. Um, so, as Dr. Bibi said, please feel free to interrupt me anytime during the talk. I can see your chat also. I guess you can raise your hand if you have any questions. I mean, I have a fair amount to go through, but I don't need to go through all of this. The slides are available, so even if I don't go through something, but you're interested in something else, please feel free to contact me anytime. Um, all right, so I'm going to go straight in. So let me see if I can. Okay, perfect. So before I actually tell you what exactly I'm talking about, let me give you some scenarios where we want to think about these problems. So here's a sort of typical scenario. So this is what I'm calling repeated online allocation. Um, and the way you should think about it is maybe there is some resource. So maybe there's a supercomputer which is available, which like students in a university can use. And each day the the supercomputer administrator needs to decide who gets to use this. So what I'm showing here is that there are two agents. So maybe these are two students, and on the first day they have a certain utility for the computing time. So they come in, and student one says, I have value 1, so maybe I just want to play games, and student 2 says, well, I have to do an assignment or something, so I have a higher value. And now what the system administrator does is they take the supercomputer time that day, and then they divide it between the agents. So here we're taking this time and we're saying, okay, maybe 2/3 should go to the second agent, 1/3 should go to the first agent, or some such other formula. And then the next day, student 1 suddenly realizes that the deadline for the assignment is here and they need to do the assignment. So they have a much higher utility. Student 2 is already ahead and so has a lower utility. Again, the system administrator can decide how to divide, and this goes on each day. So each day, the two agents, or how many ever agents you have, they have some utility, some sort of numerical value for how much the computing time is useful for them. And in the administrator gets to know this at the beginning of each day and then must decide how to split this resource. And so you have 1 unit of the resource and you can divide. And the assumption is that each agent has a utility which is proportional to the value they have in day t times the fraction of the resource they get. So VAT times XAT for agent A. And the total utility an agent gets over time is the summation of this VAT XAT over all days. Any questions about, or please feel free to sort of stop me if any of this is unclear. I'm going to give you another setting which is very similar, and in some sense I'll sort of talk about both of these. So in the second setting, it looks almost the same. Well, I've used the same pictures, but the difference here is I'm now going to assume that this budget, this resource is actually budgeted. So what I mean by that is the resource of 1 unit is available at the beginning of, say, 1 day, and then you must give it out that day. So this could be something like, so maybe you have an airplane and you're selling seats on the airplane, and you have like 1 unit of seats. So maybe think of this as 100 seats, and then each day some agents show up and they say how much utility they have for this resource. And again, you need to divide, but now I'm assuming that the resource is like you need to decide how much to give to each person on each day, and then the resource gets depleted. So okay, I've slightly changed the numbers here. So I'm starting off with 5 units of the resource. Agent 1 says he or she has value 1, agent 2 has value 2. I decide how much to give each of them. And maybe what I'm doing is I'm giving 1 unit to agent 2 and 0.5 units to agent 1. And so now the total budget has gone down to 3.5. Day 2, only agent 2 has, or some other agent comes in with some value. I give them some allocation, and this keeps going on. So I give 1 unit to this person, the budget gets depleted again, and so on and so forth. So the main difference from the previous case is this is a little more complicated because the the resource is constrained across time. So there's the total amount of resource. So you should think of this as something like a reverse of a knapsack problem. There's a total amount of resource at the beginning, and now you're giving it out to each agent. And again, the agent in agent A, if they come in round T, they have some value, let's say VA. If you give them XAT units, this could be perfectly divisible, then the utility is VA times XAT. But now the budget constraint is the sum over all time and sum over all agents of what they get. Okay, so these are sort of very common settings. So any of you who have looked at any sort of sequential decision making, Markov decision process, any of these things, online control, you would have seen settings which look like this, where you are either giving out resources each day and the resource gets regenerated, or you have a fixed budget of resource and you're giving it out. What I haven't told you up till now is, well, this is just the setting. What do you want to optimize over here? So what is your objective in a problem like this? And it turns out that the objective actually depends a lot on what you're using to model, what you're using this model to capture. So this exact same problem, if I was using it to think about something like, say, hotel rooms and travelers in the case of repeated resources, or say airline seats and travelers, if you just had a fixed amount of resource, well, the natural thought would be that the company which is selling the hotel rooms or the airline seats, they're private companies, and so maybe they care about their revenue. So you want to maximize, you want to sell in some way so that you maximize the revenue. But I can use exactly the same mathematical model to think about something like a conference room which is being shared amongst, say, faculty or students in the university. Again, each day the conference room is available, but who gets to use it has to be decided by some central planner, or maybe this is a supercomputer. Each day you have a certain number of hours that you can use the supercomputer, but you again need to decide who gets to use it. And in this case, it's quite likely that revenue is not the right thing to look at. These are shared resources. There's a sense that all the faculty or all the researchers have the right to use the resource. And so maybe what you want to look at is something like the total welfare. So what's the welfare? Well, I look at every agent, I ask them how much utility they got, how happy they were with whatever allocation they got, and then I add it up over all the agents. And you can again try to maximize this, although and there is a long history of people of a theory of trying to maximize this, but usually this involves using money, and you may complain about that. You may say, well, if this really was a conference room in a university, maybe I don't want to use money to divide it. Like, it's okay to try and maximize welfare, but like perhaps using money seems wrong in a setting like this. So that's sort of already one complication that comes about. The thing that I really want to talk about are settings like this. So I've been doing a lot of work, and I'll talk a little bit about this with like local food banks and like thinking about things like food donations and how you can decide who gets food donations where. And or another thing that happens over here, and I'll also talk about this, is like the food banks go out every day with a certain amount of food, and they go to different towns and they're distributing it amongst people who are asking for food. It's the same underlying model. So there's really nothing in principle different between like parking spots, airline seats, hotel rooms, anything of that sort, and food donations in a food bank. But it's kind of clear that you don't want to think about things like revenue and welfare. Like revenue for sure seems like the wrong thing to do when you're talking about like items which are donated. Even welfare seems wrong. So if somebody says they have a high utility, is it okay to just give them food and not give food to anyone else? Is it okay to make like other people like suffer because just someone happens to have a high utility for whatever reason? And so really the large part of this talk, my question is going to be, or what I'll try to discuss is, well, what is the objective we should be looking at in a setting like this? So we're very used to thinking about revenue and welfare. That seems like the wrong thing to do in a setting like this. Well, what is the right objective? And this, I actually think, is a really important question. So this is something I've been thinking about now for close to 5 years. back in 2015, the United Nations sort of released a list of what they call their sustainable development goals, and sort of the second one, in some sense, like close to the most important one, was this question of like just ending hunger in the world, and there's a problem which everyone in the world suffers from. Where most of us are lucky that this is not a problem that we have, but it's very easy to like just step out a little bit, and you'll see that there are people who have problems with this. Personally, I mean, this is I come from Bengal, and we are sort of, I don't want to say known, but like there's been a history of famines in Bengal, and caused due to various reasons, and like this is an important problem back home, but it's an important problem where I am today as well. So um, even in the US, despite it being highly developed, food insecurity is still a big problem. But there are some amazing organizations which sort of are working on this. So I'm guessing many of you wouldn't have heard of Feeding America. So Feeding America is it's a non-profit organization in the US which basically acts like a marketplace. So what they do is they sort of go to all the big companies throughout the US, and they say, okay, like, do you have food donations? And so you could be like a big, like a Nestle or McDonald's or some big company somewhere, and like at their factories they produce a huge amount of food, but they also have a huge amount of waste. And what Feeding America does is that it collects all this waste from like food waste or food donations from these big corporations, and then passes it on or matches it up with all the local food banks, all the local organizations which are helping to sort of take care of food insecurity in local areas. Um, and it's an amazing organization with a lot of like really impressive sort of operations research, sort of inventory planning, which is going on in the back end. But even at the more local level, there are these food banks which sort of are the next level in this process. So I live in so I work at Cornell University, which is in an area of upstate New York, which is called the Southern Tier. So this is the area sort of close to the border with Canada, and the local food bank in this region is what's called the food bank of the Southern Tier, and this is an organization we've been working a lot with over the last many years. And they what they do is they're sort of the next in line after Feeding America. So they get these donations from Feeding America, but also from like other sort of food donors, and then they go to all the different cities and towns in our local area, and then distribute the food to people here. Um, so this is a practical problem. This is something these companies do genuinely have exactly the same model which I gave in the beginning: repeated allocation without budgets, and they're all sort of thinking a lot about, okay, what is the right way to do it? What are the right rules? What are the right kind of objectives that we need in order to solve this problem? Um, any questions up till now, or any comments? Okay, again, please feel free to stop me anytime. So I know I haven't yet got technical, but from the next slide onward, I promise you it'll get a little more technical. Okay, so let me go straight in. And so there is a history of thinking about fairness, and this goes back a long way. It's been discussed a lot in philosophy over the years. More recently, in a more mathematical framework, this has been formulated going back to the 60s. But typically, when people start thinking about questions like fairness and equity and things like that, they usually think of this in a one-shot setting. So what I mean by that is, imagine all the items were available and all the people were available, and you're trying to decide which items go to which people. Um, so in this case, let's say I have n items, which are these blue circles at the bottom, and these are all divisible. So it's like 1 unit of each item, but you can sort of divide it in any fraction that you want. And you have m agents on top. These are these strange shapes on top, like all these polygons. I just want to show all these items, and all these agents are different. And each agent A has some utility VAI for item type I. And what that means is if you give them XAI units of item I, then they get a total utility of VAI times XAI for that item. And now their total utility is the sum over all items of the utility they get from each item. And as before, there's a sort of natural budget constraint that the total amount of item I give for each item, the total share of that item I give to the agents is at most one. It's the capacity of the item. So So there's the same two settings as before, except now it's completely static. So it's a one-shot problem. It's an optimization problem. You can write down these are the constraints. Um, and what I want to understand is what's the right objective which captures fairness. And what people, when they started thinking about it, they actually realized there are many ways of doing this. So unlike something like welfare or revenue, where it's very clear what's the right answer, um, it doesn't seem like there's one unique way of modeling fairness. And let me actually give you sort of a sense of like three completely different approaches to this question. So here's the first one. Same setting, but what I could now say is, and I'm guessing this is something which many of you would have thought of when I was asking this question. Maybe what I should do is I should come up with some new utility function which is more fair than just looking at the sum of utilities. So one of the original ones that people thought about is, well, let me just maximize the amount that the minimum agent gets. So this is something called the maximum utility. This is a good concept in many settings, but it's actually highly problematic in many other ways. So I mean, I'm happy to talk more about why maxmin, like what are the pros and cons, but like in a certain sense, we now understand maxmin is a really bad objective for most things. But there's this second objective which has actually been rediscovered many, many times. And this is the idea that instead of looking at the sum of all the utilities, you look at the geometric mean. So you look at the product of all the utilities. And if you want to normalize this, you sort of take the geometric mean. And this turns out to be remarkably good in many ways. So it's such a good objective that, like any good thing, it's been discovered many times independently. We think independently. So in economics, this is sometimes called the Nash social welfare, because this was one of the many contributions of John Nash, where when he was thinking about fairness, he sort of came up with this. But there was actually an even older history in economics where people started thinking about this from the point of view of bargaining theory. So it comes about through what's called the Rubinstein bargaining paradigm. In engineering, this objective is sometimes called the proportional welfare objective as opposed to maximum welfare. It's not obvious looking at it why this should be called proportional welfare, but if you sort of like look at its derivatives, there's a sense in which this seems to be proportionally balancing everyone. But maybe the simplest way to think about this is if I give you a set of people, all of whom are the same, and then you try to maximize the the best thing to do is try to make all the utilities as equal as possible. So even if they're not the same, even if they're different, you ideally want to balance everyone's utility. You want to make them as equal as possible in order to maximize the product. So this is approach one. Now, here's an objective function. And it's not an easy objective function, but this is still actually convex. So you can take log of this and you get a certain convex program called the Eisenberg-Gale convex program. You can solve it and you get sort of kind of meaningful answers from that. So that's one view of fairness. Just treat fairness as the same as welfare, just redefine the notion of welfare to be more fair. Here's a completely different view of how you can try to make sure that allocations are fair, which is, well, don't try to even solve an optimization problem. Instead, just set up a market. So what you can do is you take all these agents, give them all an equal amount of some currency, a fake currency, so that they all have an equal amount, so some number of tokens, and then let them negotiate amongst themselves. So they can discuss with each other, they can convince each other who wants what, and they can sort of pay for that. Like by doing this, you will come up with prices in this marketplace, and then people pay, but they have a fixed amount of currency, and they buy whatever they can using these prices. And so in economics, this concept is sometimes called the Fisher market, and this particular thing. Okay, so I'll come back to this question in a second. So this concept is sometimes called the Fisher market, but this particular idea of giving equal budgets, it's sometimes called the competitive equilibrium from equal outcomes. So you'll often see it called CEEI. And it seems like it's naturally fair because everyone has the same amount of money. Okay, so there's a question about information in this setting. And throughout this talk, I will assume it's full information. So I'm going to always assume that all agents know each other's utility. Um, but in some sense, in a marketplace, you don't worry as much about that because assuming the sort of efficient markets hypothesis, and yes, there are problems there, but assuming people can sort of negotiate with each other, there's a sense that if everyone is smart about it, in some sense, the best thing to do would be to share information and let the markets reach their natural price. But this is not completely true, and I'll come back to this question about incentives later in the talk. But this is actually one of the questions we would like to understand, that in something like a Fisher market, where everyone has this weird fake currency which is not real money, um, how would you how do you sort of take care about these about incentives? Yeah, okay, so that's a I thought that was a question. So the question is, do we know the values or do we know the distributions? What I'm going to assume is all agents know each other's distribution at each time, but on the sort of the day where you go to the market, in some sense, so if I'm trying to bid for today, then I know my own valuation, which is kind of the typical way you think about this in economics. But actually, as we go later on in the talk, I'm going to start assuming that we actually know the valuations. Like in some sense, the optimization problem is much harder here. The incentive problem is even harder, and in some sense, we don't really know as much about the incentives, but like the optimization is difficult enough. Um, so there's a really good question in that I'm not going to be very formal about this, but for the rest of the talk, you should assume that sorry, all the valuations are known to everyone, and we're really trying to understand how do we define fairness without worrying about incentives. But I'll try to talk a little bit about incentives. If if you want, but I'm happy to discuss this more in more detail later. Like that's a sort of much longer question. But yeah, thank you for that question. Okay, here's my kind of economic. Oh, sure. So my economic view of fairness is everyone has an equal amount of money. That's clearly fair. They can use this to try and decide what is most important for them, and I mean it just seems intuitively fair because everyone has the same amount of money. There are problems with this, but still, it's a really persuasive notion in many senses. Okay, so that was my second notion. Here's a completely different notion, a third notion of how to define fairness, which is, well, maybe I shouldn't think about a market and maybe I shouldn't think about an objective, but what I should do is I should try and figure out from a philosophical point of view what's the right way to think about fairness. So can I come up with a purely axiomatic characterization of what properties I want our distribution to have? And here are kind of two really natural properties, if you think a little about this question, that you would come up with. So, well, the first one is what's called Pareto efficiency. So I don't want it to be efficient. I don't want to maximize welfare, but I do want that whatever solution I have, I can't improve anyone's utility without making anyone else worse. So in some sense, should not have any waste in my overall problem. Like if I shouldn't have leftover food ideally, because I can take that leftover food, give it to someone, and nobody else is unhappy about it. So I would want a Pareto efficient solution. But Pareto efficiency on its own is very weak. So if a food bank can take all its food and just give it to one person, and that's Pareto efficient, because that person will be very happy and will sort of eat a lot and not worry about it. Everyone else is unhappy, but you cannot make anyone else happy without making that first person unhappy. So Pareto efficiency, it's desirable, but it doesn't seem enough. But here's this second property, which is what's called envy freeness, which actually comes in and fixes the problem. So what envy freeness says is, well, not only is the overall allocation Pareto efficient, but also if you ask any agent if they like their own allocation or if they like somebody else's, they all prefer their own allocation, or at least weakly prefer their own allocation compared to anyone else. And so that's why this is called envy freeness. So the idea is that under the final allocation, no agent envies anyone else. And envy freeness also isn't good enough on its own. So not giving anything to anyone is envy free, because if none of us have anything, we don't envy anyone else. But amazingly, if you ask for both Pareto efficiency and envy freeness together, and you can think a bit about this, but that's actually quite a powerful concept. Like when put together, it actually leads to object or allocations which seem fair, where you're not wasting anything, you're doing the best you can as a central planner, but nobody envies each other. Okay, so what I've sort of said is here are three ways of thinking about fairness, and I'm at least hoping at this point you're convinced that the problem isn't obvious. Like I'm I'm hoping even if you each have your own favorite one amongst these three, that okay, should you take the product of utilities? Should you give everyone equal budgets and have a market? Should you look at some sort of axiomatic characterization? It's not even obvious how we can compare these, right? Like they seem to be coming from completely different worlds. Like one is optimization, one is economics, one is philosophy or mathematics. And like, how do we even say one is better than the other? Um, and in some sense, this is really what makes thinking about fairness more challenging than any of like other questions in economics. Like when you want to think about these problems, you have to go back to the first principles and you have to sort of grapple with even like how do you write down the right problem before you can even start solving it. Okay, so this is a good time for a pause. So any questions about these objectives? Is it clear what? So, I mean, again, this is not exhaustive. There are other such ways of defining fairness, but in some sense, I like to think of any fairness definition as falling in one of these camps. It's either optimization, economic, or axiomatic. Okay, so why have I picked these three particular definitions? Why did I pick geometric mean? Why Fisher market? Why Pareto efficiency and NV free? Well, these three are actually somewhat special in that it turns out that for many settings, these three are actually exactly the same. So in particular, as long as the resources are perfectly divisible, so as long as you can sort of take any fractional XAI, and the utility function has a particular form. So for example, what I've given over here is this is what's called a linear utility function. The theorem is actually much more general, but it definitely works for linear utility functions. So as long as you have divisible items and linear utility functions, there's an amazing theorem by Havarian back in the 1970s where basically proved that the allocation that you give under each of these. So clearly these don't have the same, say, objective value. They don't even have an objective in many cases. But in each of these cases, there's a unique allocation, which maximizes the geometric mean, which is Pareto efficient and NV free, and which is the solution to the Fisher market. And this allocation turns out to be exactly the same. And I actually find this quite an amazing result because what Varian is doing over here is he's saying, well, you don't need to take a position. You don't need to decide whether you want to think of yourself as doing optimization or economics or philosophy. The magic of kind of formulating this problem mathematically and studying it is that you realize that all of these completely diverse viewpoints are exactly the same, but in a very particular setting. So it's same as long as it's divisible items and under some utility functions. So this being such an amazing result, I felt I should actually show Halvarian. So here's Halvarian. He's actually now, I think, the chief economist at either Microsoft or Google, somewhere big. So this is not at all like his most famous work. He's known for much else, but at least for me, this is one of his most amazing contributions to like, modern economics, modern life in general. That this paper, you can actually find the paper online. It's like MIT has uploaded a version of like, the original text report. It's a very simple paper to read, but you essentially get this remarkable theory. Any questions? Or is there anything anyone wants me to explain in more detail here? Okay, so if not, so what is this talk about? I mean, I've told you about Halvarian's work. What's the problem? Why do we need to still talk about this? Why do we not just agree this is the solution? And the problem is this little bit over here, divisible items, linear utilities. That actually turns out to be crucial. So as soon as I relax these assumptions, these theorems don't hold. Um, if you have indivisible items, if you have sort of integer constraints, we can no longer do this. But what's more interesting for me is this really does assume you can decide this allocation upfront. As soon as you have a sequential setting, so let's say you have items arriving over time or people arriving over time, there isn't a natural generalization of variance result. And in some sense, my sort of research agenda in this direction has been to try and think about like what is the right way of thinking about fairness in sequential settings. And let me sort of give you a sense that in online allocation, if we try to do these same problems, if we try to think about what is the right way of thinking about fairness, well, I can still take the economic viewpoint. Um, and the way you would implement the economic viewpoint is you would create an artificial market. So you give everyone some amount of okay, so there's a question about okay, which of these viewpoints have more efficiency? What I'm actually pointing out is something more remarkable, which is they're all identical. Like each of these viewpoints, if you solve for what what solution they will literally give you exact same solution. So if I solve the optimization problem and look at the vector of allocations, that is going to be the outcome of the Fisher market, and that is going to be the unique out like vector which is Pareto efficient and envy free. So in some sense, these three viewpoints are identical as long as you believe, as long as you're in a setting with divisible items and one-shot allocation. Does this make sense? So that's why I'm saying, at least in the simple world where we're we're not doing things over time, there's no difference between these. But your question is really prescient in that that's a good way to understand what goes like if I go to a setting where this theorem isn't true, this would be a natural question to ask, like which of these ways of actually solving the problem is more efficient if, let's say, you have indivisible items or if you have sequential allocations. And I'll talk a little bit about that. But is it at least clear that in the static setting, these are the same? Yeah, so that's an amazing question. So the question is, so is there always a Pareto efficient and envy-free allocation? Yes, and this is totally not obvious. So that's kind of a corollary of variance result that these two properties I gave you, maybe they're never satisfied. But amazingly, for divisible items, linear utilities, there is always an allocation which is Pareto efficient and envy free. But more remarkably, there's actually a unique allocation which is Pareto efficient and envy free. There's only one, and that just happens to be the solution of the Nash social welfare. Any other questions? I mean, I'm actually happy sort of emphasizing this more than my work. I feel like there's a sort of less understood corner of economics which really should be more understood. Okay, I'll keep going on, but please feel free to sort of stop me. So let me give you some sense of, yeah, like how do you do this in practice in a sequential setting and what goes wrong? So the way you would implement a Fisher market in practice is you give people artificial credit. So you give people some number of tokens, say each year, and then basically set up a marketplace. And this is how the food banks in the US at least are organized. So this is what Feeding America does, where this is actually Feeding America's like eBay backend in some sense, where they've given everyone. So if you look over here, this is a food bank in Los Angeles. They have these 9,500 points. Points are kind of the artificial currency that Feeding America has created. And now each of these items, there's basically an auction for this. So here's item description, here's how many boxes there are, here's what the current bid is. It's basically like eBay for food supply, but with a fake currency. And the problem now is it's actually not clear if this is good. And this goes back to the question Amin asked earlier, which is, if I create a market like this where I give you these fake currencies, well, what can you do with fake currencies? You can't like take the fake currency and go and buy coffee with it. You can only use it in this market. And so there's a sense in which this is no longer actually linear utilities. Like it's not the same as money in a certain sense, and so we are not actually sure if it's efficient, or like if people will tell the truth using this. And in some sense it's clear they won't tell the truth. If I give everyone 100 tokens and then have a single auction, each of you will bid 100 tokens. Why would you not? The tokens are not useful for anything else. um, but one of the things that we showed, so this was something which we've studied a lot, and one of the things which we showed is, in a Bayesian world, so as long as everyone knows everyone else's distribution, and you do run the system over time, so you don't run it for one day, but you run it for 1 year using the same amount of, like using the same currency, like the same budget for every day, like you have a total budget which you have to use over the entire year. Then you can kind of use ideas from like concentration and like stochastic processes and show that these are not, they're not optimal, they're not efficient and truthful, but they're almost efficient and almost truthful in a formal sense. So I have a series of papers trying to understand this. It's actually also true if you don't know the distribution. So you may complain that how would I know what's the distribution of some other food bank? And it turns out that you can still say something if you don't know the distributions. You can give some guarantees about like how robust these solutions are. So in particular, doing something as simple as a first price auction with a fake currency is guaranteed to be at least half robust in a certain formal sense. And I'm not going to talk more about this, but like basically we have good mathematical reasons to now believe that these fake markets actually work. But in practice, in reality, we know they work really well. Like this is even without all of this theory that I have. We have really good empirical evidence that we being like Feeding America and other people who use it, that these marketplaces are amazing. Um, but they are problematic. I mean, okay, so I actually have a bunch of talks on this. If anyone's interested, I'm happy to point you to this. Um, but there are problems. So one big problem in doing something like a artificial currency auction is, as a central planner, you actually give up all control. Like if I'm giving everyone fake currencies and asking them to do whatever they want, um, I can't go in and change things afterwards. So I can't go in and say that no, this wasn't the right answer. So let's say I was using this for something like vaccine allocation, and I realized that people are cheating. Well, it's out of my hands. As a planner, I can't do anything. I've given up all control. So the sense in which that is not a great idea. Now, on the other hand, maybe what you want to do is you want to use some kind of optimization approach, and this is done. So this is done a lot in practice. So in like networking, there's this notion by Frank Kelly of like using proportional fairness for doing scheduling, and it's really popular in many settings. Um, and we also have some work on looking at this problem and trying to understand like the competitive behavior of this. So what can you do again if you don't have any Bayesian assumptions? If these values are truly arbitrary and you still try to maximize, say, the Nash social welfare, then how well can you do it? Sort of short stories, you can get something like a log t approximation, and this is the best. And most other objectives, so something like max min is actually really bad in this sense. Like you can't even get close to like better than square root t, whereas Nash social welfare, you can actually get pretty close even without knowing any information. Um, but there's again a problem, which is that if I try to approximate an objective, but I can only approximate, like, I cannot get it exactly. So if the exact objective had a certain fairness property, the approximate objective may have no good property. And one good example of this is, suppose I give you a solution which is on average fair. Well, I could give you like 100 units on one with probability 1 over 100 and 0 units. This on average gives you 1 unit, but I mean, it's very different from just guaranteeing that you get 1 unit every day. So in some sense, any kind of approximation for an objective function really destroys any of the fairness properties that it has. And so given we knew that these problems existed, we sort of, over the last few years, came back to this question and started asking the question, okay, like what can we say about the axiomatic viewpoint? So the economic and the algorithmic viewpoints are powerful, but they seem to have limitations. So when we actually go back to first principles and ask, what does it mean to guarantee kind of envy freeness and efficiency in these problems? Great, thank you. Okay, so what I'm going to tell you in the rest of the talk is a little bit about, going back to thinking about just axiomatically what is the right way to think about fairness in online settings, and what sort of interesting optimization problems come about when you think about doing this in a sequential setting. Um, and And this is the work which we've been doing in practice. So this again is the Food Bank of the Southern Tier who've been working with. And what they have is this thing called the mobile pantry, which is basically a big truck, which every day in the morning they load up with as much food as they can. And then they go to each of these like neighborhood villages and like towns, and like we are in a somewhat rural area. So there are like a lot of small like villages and towns around here. And you go to like multiple places each day, and then you kind of try and distribute the food. Um, wouldn't surprise most of you to learn that, as usual with anything like this, the demand is much more than the supply. So there's usually a shortage of food, and the food bank isn't able to give as much as the demand is in each location. So they need to decide how much to give. They need to decide at each location what's the right amount of food to give out. And and so what we started doing is we sort of started working with the food bank on trying to understand this problem, and in particular trying to think about like how close can we get to these notions of Pareto efficiency and envy freeness. So in particular, we kind of went back and looked at the literature, and we saw that all the notions that people had thought of were really problematic in certain ways. If you just looked at what the allocations were, um, they didn't seem to like, even though they had certain guarantees, they were very far from like how we would think about them being like Pareto efficient or envy free. And so what we started doing is we said, okay, can we at least understand in hindsight? So at the end of the day, once we know all the demand, um, how close can we get to Pareto efficiency and envy freeness? So what do I mean by this? The problem is in all of these settings, each like whenever I go to a location to give out food, I don't know how much demand is going to be there in later location. So if I knew all the demand, this would just be a static problem. I could use variance result. Um, but I do know the demand at the end of the day. So at the end of the day, I can sort of look back and say, oh, this was how many people showed up in each location. Well, what would I have done if I knew this information in advance? That's something I can calculate. And now I can use this to try and score how well I've done. I can look at what allocation I actually gave out and say, well, how close are you to this ideal allocation, which I know is unique because of variance result. Um, and this gives this a really interesting control problem where it's a really high dimensional problem where you're trying to compete against this counterfactual notion in hindsight. And surprisingly, what we could do is like we could actually figure out the optimal way to do this, but it actually leads to new policies which are just much better than anything we know for this problem. Um, so this is joint work I did with my colleague Christina Lee, the picture on the right, and our PhD student Sean Sinclair, who's the person in between, and also there was an undergraduate student Gauri Jain who was working with us, and she's now actually starting a PhD at Harvard. And we've kind of got two papers. The first one is more of an empirical paper to try and suggest that this is the right way to think about fairness, and then the second one is more about the kind of coming up with optimal policies under this notion that I'll talk to you about. So like both of these are available on archive. I think they're also on my website. I'd love to get any comments anyone has on this. So here's the model that I want you to think about for the rest of the talk. So I have an initial budget B. There's this mobile pantry which has a certain amount of food. This food is perfectly divisible, and there's just one type of food. It's just like food units. And this pantry is visiting each location. So they're visiting T locations one by one. So like T different villages in this area. And in each location, they go there and then they see how many people have showed up. So usually the mobile pantry says that we'll be coming at 11:30 or 1:30 or whatever, but they don't know how many people will show up on each day at each place. They have some historical data, but they don't know the exact amount. So there's some number NT of people who show up in location T, but this is a random variable drawn from some distribution FT. And for simplicity, we don't need this for the paper, but like just for the talk, I'm going to assume that every person has the same utility. So if you give them xi units of food, they get the same utility vi xi. It's identical no matter who the person is. And so now here's a question, and I'll actually throw it out to everyone in the audience. So suppose I told you, so every person is the same. And let's say I knew exactly how many people were coming in each location. So at the end of the day, I know, like I went to 10 places. In the first place, there were five, second place, six people, third people, etc., etc. So given that I know the total amount, or like the number of people in each place, so in particular the total amount, does anyone have a sense of like, what do you think is the fair amount to give each person? So I have 100 units of food, and let's say I know that a total of 50 people came spread across all of these different places, these different villages and towns. Um, how many units should I give each person? If I had known this in advance, how many units would I give each person? Any thoughts? So just even forget all the definitions I gave. Like, what would you think is the right thing to do? There are 100 units of food, and I know 50 people came at the end of the day. Yeah, I would. So I'm guessing you're saying I would give 100 divided by 50, so like 2 units to each person, right? And this seems natural, right? Like, um, if this was the only thing I told you, and assuming all people are equal, feels like that's the only thing that would make sense. Now, as an aside, variant solution, and in fact, all the three notions I gave you in this particular setting, if you solve it, you would get 2 units as the unique answer. So that hopefully convinces you that this is meaningful. And so what we're saying is, yeah, in hindsight, um, the correct amount ex post, so ex post means in at the end of time, would be to give everyone b over n, which was 2 units of b was 100 and n was 50. But like if I know the total number n, I should give everyone b over n. And so what we said is, well, let's look at two metrics in hindsight, which are firstly, how far away was each person's allocation from b over n? Like, who was the person who got the maximum amount of food? Who was the person who got the minimum amount of food? What's the distance from b over n? Now, clearly, everyone cannot get more than b over n. Everyone can't do more than the average. Similarly, everyone can't, but everyone can be less because I can give out less food. I can always hold back the food. Yeah, so I haven't said how I can do this. So yes, we do need to prioritize people in various ways because some people are coming earlier and later. But all I'm suggesting is, at the end of the day, if I know how much food I give each person, then looking at how far away that number is from b over n is a meaningful way to think about how good a policy is. So a policy which gives 2 units to each person is much better than, say, one which gives 1 unit to some people and 3 units to some people. And it's much better than giving 0 units to most people and 100 units to some people, even though maybe they're the same in expectation. So that's property one. But property two, which I'm going to look at, is, well, how much food did I waste? So maybe I don't want to give out all the food, and you may say, okay, wait 1 second, why won't you give out all the food? Well, what if I made a mistake and I was assuming that there would be 10 people in the last location, and so I have 20 units of food left over, and like I did my calculations perfectly, I have 20 units of food to give in the last location, but only one person showed up. Should I give that person 20 units of food? That would sort of destroy my envy freeness, right? Like people would say, well, that was unfair. We all got 2 units. Why did that person get 20 units? So in some sense, it's I have the ability to waste food, and there's not even waste. I have the ability to not give out all the food. Like this food is not necessarily perishable, so I can hold some back, and this could be important in many settings. But even more importantly, like both of these quantities, NV and efficiency, the delta NV, delta efficiency, these are scores which I'm giving my policy in hindsight. So I'm looking at the entire realization of my sample path, and then I'm executing my policy, and then I'm saying this is how well my policy did in hindsight. So these are random variables which depend on the actual sequence of arrivals and what allocation I give. And okay, so here's the sort of formal model that, yeah, I need to do these allocations, but really what I want to understand is how well can I do with these two metrics? So can I come up with policies which are low on delta NV and or low on delta efficiency? And it's actually not trivial. Even minimizing delta NV is tricky because I don't know B over N. If I knew N, then the policy is easy, but I don't know N. So I need to somehow guess what it is, and my guess keeps evolving over time. So I'm going to skip this, but basically what I'm saying is we can solve this instead of looking at b over n. If I give you a more general utility function and like multiple items, there's still a way of defining this notion in hindsight, which is by solving the Nash social welfare. So sort of taking variant solution, solving it in hindsight, and looking at the unique solution that you get, and then looking at the distance from that unique solution and also how much I waste compared to that. Um, and here's sort of the main punchline of the work which we did, which is if you think about these two quantities, the gap from B over N and the amount of waste, then it turns out that they actually satisfy a certain form of an uncertainty principle. So what do I mean by that? Um, Firstly, on the left-hand side, what you can see is on my x-axis, I've looked at the gap from B over N. So the gap from the fair allocation in hindsight. And what I'm saying is there's always a minimum gap which has to be there because of noise. So I can never predict B over N exactly. And so no matter what allocation I give, I can never do better than 1 over square root t compared to B over N. This is just the central limit theorem in a certain form. Like it's saying because of the uncertainty, I have to give something to the first person. I'm trying to guess what N is, but I don't know N. And so because of that uncertainty, I'm never going to, I'll either give too much or too little. I can never give the right amount exactly. But what's a little more remarkable is that if I look at the product of these two things, so if I look at the amount of food that I waste and the gap from my optimal solution in hindsight, then for any solution which is online, so any solution which just knows the distributions and is making decisions as it goes along, the product of these two is at least a constant. So if you try to reduce the amount of waste, then you will increase the amount of the sort of variability, the envy. If you try to reduce the envy, you'll increase waste. And in fact, one extreme, which is really easy, is not giving anything to anyone is envy free, but it has a huge waste. You're sort of holding back all your food. In fact, that has linear waste. What this is saying is like, whatever amazing policy you come up with, there's always this trade-off between the two. The product is a constant, but what's even, that's kind of the negative result. The positive result, which is what we're more excited about, is everything outside this region is actually achievable. So there's a very simple policy, which is something called guarded hope, and I'll try to briefly sort of talk about this, but every point in the envy efficiency uncertainty trade-off can be achieved by sort of a particular version of this algorithm. Let me show you how this looks in practice. So this is sort of looking at the food bank data, and what I'm showing you on the left is I'm increasing the number of rounds. So I'm sort of looking at 10 people, 20 people, like 10 rounds, 20 rounds, 100 rounds, 200 rounds. Maybe you can think of doing this over time. And I'm seeing how this gap from B over N is changing using like different forms of this policy. So this policy that we have, it has a certain parameter which you change, like a hyperparameter. And you can see in all cases it's decaying, but the decay rate is different. So the blue curve has a decay rate of 1 over square root t. Also the orange curve has a 1 over square root t. The green curve has a 1 over cube root of t. So it's decaying slower than the blue and orange curves. But on the other hand, you can look at the waste, which is the picture on the right, the two pictures on the right, and you can see that the blue and orange curves have sort of worse waste than the green curve, at least in most cases. And that's because the product of the two, the rate at which the first curve decreases and the rate at which the second curve increases, that product is a constant. And you're actually achieving every point in this space. So I'm going to take like maybe just 2 minutes to quickly explain the policy, and then I'll stop for questions, but I'm happy to sort of stay on longer and say more about this policy. So what exactly is going on in this policy? So I won't talk about the lower bound, but sorry, here's what the policy looks like, and it's a very simple idea. So the idea is the following. I have some uncertainty about what's coming in the future, but what I can do is I can sort of scale back a bit. I can say that even though I don't know the exact number coming in, I don't know that the number is 50, I know it is at least 30 with very high probability. Sorry, it's the other way. I know it is at most 80 with very high probability. And you can just get this from a central limit theorem argument. You can sort of say, I know all the distributions. If I add up the distributions, here's the tail of the distribution. Like with 99% probability, I know that there's less than equal to 80 people showing up. Once I know that, that gives me a lower bound on what the right answer is. So it says the answer may be, I don't know, it's 100 divided by 50, but it's at least 100 divided by 80. So it's at least like yeah, it's like at least 10 over 8. So now I can promise everyone, look, I don't know what's the exact amount I'm going to give you, but I'll at least give you 1.25. You're all guaranteed you'll get 1.25. And I'm sure that with 99% probability, if I give everyone 1.25, everyone will get food. They will get 1.25 units with 99% probability. Now, after I do this, I have some amount of food left over. Or like as time goes on, I realize that the number of people coming in is more or less. And what this means is I have some kind of excess amount or some excess or deficit of food on top of the mean. So I'm sort of looking at the fluctuations about on top of this minimum support level. So I'm giving everyone 1.25, and at some point I realize I have slightly more food. What I can then do is I can start giving more, but I can't give too much more, because if I give too much more, then my NVE gets destroyed. So what I will give is, so what I'm showing in this picture is I'm initially giving this lower dashed line. This is what we call the lower guardrail. That's my conservative estimate. And every once in a while, if the amount of food becomes high, I switch to giving my upper guardrail. So everyone gets either 1.25 or say 2.5, but not more and not less. And I kind of bounce back and forth between these amounts. And I do this in a very careful way so that I actually make sure that I'm always within these boundaries, but I don't waste. I sort of waste the least amount of food. So for any of you who've seen any sort of control theory before, this is a form of what's called bang-bang control, but it's sort of a very carefully designed bang-bang control where I'm using these upper and lower guardrails to decide the limits of how much. So you should think of this like a thermostat, where if you ask it to set the temperature to, I don't know, 25 degrees centigrade, it'll never do 25, but it'll do like 22 and 27 and oscillate between the two. And you can do something like that with these allocations, but you have to do it in a very careful way because you have a limited amount of budget. What's more remarkable is that if you do this carefully, you can show this policy will achieve all of these curves by just tuning the distance between these guardrails. So sorry, I rushed through that part, but I'm happy to talk more about this. Like, this is a completely, it's surprising to us in hindsight that like even though this policy is quite obvious, this somehow didn't seem to exist in the literature. But like, it is something which we know is really strong. So like, if you look at this in, sorry, I'm gonna skip ahead, but yeah, if you look at this in practice and if you look at this on data, like it is just much better than any of the existing policies. And in some sense, the reason why this is true is like once we go in and understand from first principles what's the right axiomatic solution, you realize that this is the optimal thing to do. But it really depends on like formalizing this problem correctly, and that is a tricky thing to do. So the one last thing I want to say is that this problem, even though I was talking about it for one particular thing, which was for food banks, the same tension arises in many other settings. So I'm sure you've also worked on, like most of you have worked on problems where there isn't one objective, but there are multiple objectives, and you're trying to balance them. And that's really what's happening in fairness, where we're trying to balance how much each person gets. And one of the things which we've realized is one reason why we seem to get it very wrong as a field is we don't actually have good like simulation code. We don't have good code for actually just testing these policies and comparing it with each other and measuring all these objectives for these really more complicated problems. And so one thing which like me and my students have been trying to build out is like this whole sort of back-end software package for just making it easy to like solve all these problems in operations research, operations management, and look at all these different objectives and then kind of compare policies in a like-to-like way. So to give an example of this, so it's, yeah, there was an undergraduate student who was working on an ambulance routing problem, where again you have this kind of tension between minimizing some kind of average latency versus like a worst case latency. And And what you can do is you can use the software package and very easily, we have all these environments available to you. You can very easily try out different policies. And in fact, you can try out policies similar to what I was saying and then compare them for these different metrics. I'm sorry, this picture isn't very clear, but like what you can see over here is we've run many different policies and we're comparing them for different metrics. And so you can see some things do well for certain metrics and do badly for other metrics. And we kind of want to balance these. And the nice thing with the package, or like what we've realized, is people find it difficult to do this because it just takes some amount of time. And like we've just automated all of these processes. So if you're working on a particular problem and you want to compare like different algorithms and look at different objectives, yeah, I mean, we'd be very happy to talk to you about it, and in particular, sort of show you how to just automate this process using this. Okay, so all I want to talk about, one brief mention in the end. So a lot of this work was supported by the National Science Foundation here, and actually my mentor there was this amazing gentleman, Professor Kishan Baheti, who unfortunately last month passed away due to COVID. So a lot of the work that I did was kind of like he really inspired us to like stop working. So I mostly work on like things like revenue management and like ride sharing systems and kind of problems closer to the first stuff I was talking about. And like he sort of kept pushing us to try thinking about problems outside that space, like where else would be more applicable. So yeah, so a huge amount of thanks wherever Kishan is. I wish we could describe it to him, but I'm glad I got to describe it to all of you.